We're talking about like where the drinks were, where the bathrooms were, how you got from one place to another.
Was there any concerns that came up? I'm not aware of any, but Heather, are you aware of anything that came up yesterday that we need to cover today? Before. Okay, carry on. Today we'll be starting out with Andrew Dickson talking about pH and alkalinity. So, take it away, Andrew.
Thank you. I chose these two as the ones I would emphasize more. You probably don't need it quite this peaceful, but I'll try and keep you awake. I chose these two because total carbon is relatively easy. You add acid, you get the CO2 out, you measure how much CO2 you had, and we know what it necessarily ought to be. It ought to be the sum of the terms unionized CO2, bicarbonate, and carbonate. PCO2 was mentioned yesterday afternoon, and so there was some information there about what you knew, that essentially you're measuring something that's proportional to the unionized CO2 in seawater. With alkalinity and pH, I think all bets are off. Most people probably don't have a clear idea on what you would measure or even why you might reasonably expect to measure that, even for those people who know, yes, that's how you measure alkalinity. You know, why would that necessarily work? And so we're going to go in a little more gory detail about these two because they're very useful measurements for a variety of things. One, they're probably the cheapest equipment, and they're fairly reliable if you take care with calibration and quality control, and I'll talk more about that, those aspects tomorrow. So, remind you again that you can look at this, and undoubtedly it has flaws and typos, but it's probably better than what you managed to take as notes from me talking. What I'm talking about is not heavily, some of it's covered in this, some of it isn't. It's a matter of the level I chose it was to be at. If you actually ever want to make the measurement, buy the cookbook. It's available at the same great price much of this is. You don't pay anything and you get what you pay for. You can download it from a website, and I hope many of you have. The section in that chapter for the ePoker guide starts with this text. And perhaps it's appropriate to point out these parts. Unfortunately, as noted by Dickson in 1984, the field of pH scales and the study of acid-base equilibrium in seawater is one of the more confused areas of marine chemistry. Some things never change. 25 years, and I could use that, I have used that statement again. I'd used it in 1984. It's in my 2009 chapter for ePoker. And so that's why I think it's worth emphasizing this. I'm not going to tell you everything I know about pH. This will delight you, or at least it would have if I'd started, because there's an awful lot that I'm not covering. You can buy whole books on the subject. And so this is very much the short course version. So we saw this kind of picture before, and we're saying, okay, it's an acid-base reaction that we're going to get a pH from. And so it's always important to think of this pH as a hydrogen ion concentration. Typically, I think the right response is, who cares? It really is not of itself a useful number. It's useful because a lot of other things, it tells you information about a lot of other things. And for acid-base processes, as I pointed out yesterday, essentially you're looking at this equation here. That is, that the pH and the log, typo, no K, there should have been a K in there, of the equilibrium constant for the acid are related by this equation. Now, this third term is something that in principle is real, right? That is, you would know if you had an instrument that could measure it, the concentration of bicarbonate, and you would know the concentration of carbonate if you had an instrument that would measure it. My comment yesterday was most of this is because we can't measure these things directly, but in principle we could. So anything we do in the way we define pH, we have to do the same thing in the way we define an association constant for reality to stay real. That ratio didn't change, because the way you think about how you're defining pH and equilibrium constants is your mental picture. Those actual concentrations didn't change. So ultimately, that's the thing to remember, that all these various pH scales you will hear about must be considered as a package deal. The way we define and measure pH, and for goodness sake, they must have done it exactly the same way when they told you what the equilibrium constant was. Otherwise, this equation won't be true. That's why people make this emphasis about make sure you're using the right set of equilibrium constants. It's for the pH scale. It's much easier, in my opinion, to take my advice and ignore most of the pH scales. And I'll come back as I go through this as to why I think that's necessarily important. So the one that I'm going to talk most about is referred to as this, the total hydrogen ion concentration pH scale, defined like this, and definitely recommended. Now, if you stop there, it stays simple, but I'm not going to do you that favor. I'll go a little further. The brackets imply a total concentration. When I say the concentration of carbonate, I mentioned yesterday that I include its complexes with any of the components of the ionic medium that is seawater. Now, for a simple way of thinking about it, you could think of that ionic medium as being made up of these species. The water itself, the major cations, sodium, magnesium, potassium, calcium, chloride, sulfate. Those are more than 99% of all the dissolved material in seawater by mass. Thus, those dominate how the activity coefficients, the values activity coefficient have, because of the interactions between the things that are there in large amounts and the things you're interested in. In the case of hydrogen ion, it actually interacts with two of those. It interacts with the water, but you knew that anyway. I kind of talked about that yesterday. I initially wrote H3O plus as a sort of hint of that, and then gave up to save the trouble of typing it. The other one that it reacts with is it reacts with sulfate ion. It reacts with sulfate ion to form this hydrogen sulfate ion, or bisulfate in an older nomenclature. And that potentially complicates things. You'll see what I mean by the word potentially. It definitely complicates things if you're trying to establish the pH scale and make sure that the constants are defined on it. It doesn't really, for a user, complicate things. Somebody said, use this pH scale this way and these constants, and they will match, and you will be able to calculate speciation as accurately as possible as a result. But I'll just give you a little bit of what's in this, because then you can start to see and tie it into other things you've heard and learned about pH in seawater. So it reacts with sulfate ion. Typically, just for convenience, convention, I'm writing this as the dissociation of hydrogen sulfate with an appropriate dissociation constant. And to be fair, this is where it gets a little bit uglier. And the reason it gets uglier is this, that if you were to define a total hydrogen ion concentration, the way I've intimated that you might and should, it would be relatively straightforward. The concentration would simply be the sum of the free hydrogen that attached to water and the HSO4 that attached to sulfate. And the total would be the total of these two. Now, we can rewrite this equation involving the equilibrium constant. And we get this, where the total concentration is equal to the free concentration times this term in brackets. We just rearrange this equation to put it in there. So the problem you've got with this is at low pHs, the term in parentheses is not a constant. At higher pHs it is. Where do I choose low and high? pH 5. Above pH 5, that term in parentheses is essentially constant. And if it's essentially constant, you're saying that your total hydrogen ion concentration would be directly proportional to the free ion concentration, which is handy because mostly we think if you're putting an electrode or something in the water, surely it's not responding to the total. I mean, is hydrogen sulfate one of the ions interacting at the surface of that electrode? No. So it fits nicer in your mind that you think there's this relationship between the way we define a pH scale, which is for convenience, and the way it actually really works in the water, or at least your mental picture of that. And to achieve this and make sure that you do it at all pHs, you could change that equation a little. Where here, I've replaced sulfate ion concentration with the total amount of sulfate ion in seawater. Instead of the total that's not present as HSO4. Now that, in parentheses, now is a constant at a particular salinity temperature. Why would you go to this trouble? Before I go a little further, let me explain. The problem you've got is at some point you're going to want to say, I have a solution that I know the hydrogen ion concentration for. And one of the easiest ways to do that, and ultimately the way this really is calibrated, is to put a known amount of acid in a solution that was previously neutral. But if that acid partially reacts with the HSO4, you would need to know the value for that equilibrium constant. And that equilibrium constant, because it's fairly small, I mean, it's fairly large equilibrium constant. It's about 10, 15 in that region. You can't measure it very well. So in order to correct your data so that you really got free hydrogen ion concentration, you know you'd have an uncertainty because of the correction being probably wrong. Now this might cancel out with the uncertainties you did it when you did the equilibrium constants, and you could be happy, but there are other bits that come into that. So essentially what we said is, hey, don't worry about it. Just this amount of acid went into the water. It's either as HSO4 or H. It doesn't matter. Total hydrogen ion concentration. By defining it in this fashion, and I've changed that equals sign to say it's defined this way. It's exactly the same in the pH range you're mostly using it, 5 to 10. But it also works perfectly well in the area where you want this simple calibration of adding acid. And you can use it that way. So that's how this comes up. And as I say, the real advantage is this, that the hydrogen ion concentration is proportional to the free one at all pHs, which is, on the whole, how you'd want it. Now, the good news is this is the only species where I take this much trouble to talk about it. The bad news, perhaps, is that if you were thinking carefully, the same idea applies to all the other species I'm saying actually are constant in seawater. Because for that activity coefficient product to be constant, it means essentially the same thing, that the total concentration is proportional to the free concentration at all, over the whole range of conditions that you care about doing it. The reason it matters for pH is we have this peculiar system that we really want to do it in very changed circumstance where we added acid to the solution to get the calibration. And therefore, I have to be explicit about it here. I didn't have to be explicit before. So we've defined, and this defines a total hydrogen ion. How would you actually measure it? Well, the usual way you measure a pH is you buy a pH meter and a pH electrode. We can sort of represent that in this way. What you actually have, this is a conventional way of writing an electrode process. A pH electrode is all this together. On one part, you've got a reference electrode. The idea of a reference electrode is that it's believed to be a stable reference point. Then you typically have some solution that is a stable composition, which is why the reference electrode has a stable potential associated with it. That solution adjoins your test solution. This double line means liquid junction. That means really it's a liquid-liquid interface. But that's actually awkward to do. You can just about do it. You know, if you have cold drink and you pour some warm red wine carefully on the top, you can do this. But typically the way it's done in electrodes is you put a physical barrier to diffusion in the way, like a ceramic frit or something like that, that slows down the rate at which those two solutions can exchange. And you've got this intermediate region represented by the double lines where it's a mixture of the two solutions. In actual fact, that contributes some of the potential of the cell, because in that mixture ions are diffusing at different rates, and if positive ones get away from negative ones, you get a potential produced. Your test solution, the one you really care about, an electrode reversible to hydrogen ion. Reversible essentially means we get this many volts per factor of 10 change in the hydrogen ion concentration in our system here for talking about total hydrogen ion concentration. So to use this, it's relatively straightforward. You have the meter, you have the probe. And if you read the instruction, it says, you know, calibrate. And you put it into a solution and you measure a potential. That solution is a standard reference buffer. What property it has is that in that solution we know what the hydrogen ion concentration is. Well, no would overstate. We believe we. If you then take the probe and put it in your test solution, you will get a different EMF. The relationship between those two EMFs and the two pHs of your test solution and the buffer solution is given by this equation. Now, clearly you can see a simple statement, which I'll come back to with my discussion of uncertainty tomorrow, is anytime something depends on something else, it's bound to be partly wrong. So the difficulties you've got are, do we really know the pH of the standard buffer? As I said, in part we defined this to make it more straightforward to assign those pHs. So the answer is probably reasonably well if you have a certified standard buffer. If you made it up yourself according to a recipe, not quite so well. If you made a mistake following the recipe, all bets are off. A voltage measurement, if the meter still works, you're probably okay there. Every now and then they don't work, but they don't work. They still give a display that looks vaguely plausible. You know, the amplifier's not right, but you're kind of doomed. At some point you have to trust something, and a pH meter is probably one of the more trustable bits. This term on the bottom is, as I said, the amount of voltage change you will get for a factor of 10 change in pH. It's not much. It's about 60 millivolts. So that's for 1 pH unit. So for 0.01 pH units, it's going to be 0.6 millivolts. This is, you know, arithmetic you can follow sensibly. So you have to have a pretty good pH meter to get reasonable pH measurements. The electrodes have to behave perfectly. Do electrodes behave perfectly? More often than you would think, but not all the time. How can you tell? Well, we'll come back to that. In principle, if you had two buffers, that is, not only did you know this one, but you also knew that one as well, then you could test whether this was a consistent system, and your most likely place to ascribe blame normally is you say, look, this buffer says pH 4, this buffer says pH 7, but it's only 170 millivolts between the two, not 180. Couldn't I just put some fiddle factor and change that term? And the answer is yes, if you're really sure those were pH 4 and 7. The very fact you say they're 4 and 7 suggests to me you don't really know, because to get exactly those values implies that corners have been cut to a large extent. So it becomes harder to know how well you've got it, and to get this, as I said, you have to have a pH cell, a pH meter, a standard buffer, oh, and temperature control, because you've got this term T here. And you could do a quick estimate for temperature control. You know, it's not that demanding. 60 millivolts per pH unit. Temperature is about, for this kind of arithmetic, 300 degrees Kelvin, 300 Kelvin. So if you're within 1/10 of a degree, you're going to be okay. That would be my aim for pH measurements, that you had the temperature at that level. So this is a glass reference electrode. Usually, there are other devices out there. Some of them look very hopeful that they will work well. None of them, I think, have been adequately tested. The thing about a pH meter is it's really a voltmeter with a very high input impedance. The glass electrode system, because you've got a piece of glass in your cell, has a resistance of a few hundred million ohms, a few hundred megohms. If you want to measure the potential of that, you've got to have a circuit that can do that without putting much current around the circuit, because if you put current on the circuit, you electrolyze the water right at the surface of your electrode. The pH changes right where you're electrolyzing the water, and you get the most interesting results, but probably not the ones you were hoping for. So pH meter is a high input impedance system, and you probably want it to read to plus or minus 0.1 of a millivolt. Can you really rely on the data at that level? Hell no. But the next level up is plus or minus 1 millivolt, and that doesn't leave you quite enough maneuvering room for seeing problems. You need a standard buffer. The only one that you're likely to come across is what I will refer to as tris in synthetic seawater. And I'll come back to that because it's obvious. There are other buffers you can make, but it's more of a problem. Temperature control, you need about 1/10 of a degree. So this is actually quite manageable, because a decent set of electrodes, $200 or $300. Decent pH meter, well, they'll probably give you one if you bought an expensive balance. That's how I acquired one. But otherwise, you'd pay about $1,000. Standard buffer, you can make it or get some off me. We'll come back to that. Temperature control, you have to have some way of doing this temperature. if you're not controlling temperature, that is, if these two measurements are made at different temperatures, and those buffers are actually acid-base systems, so the pH changes as a function of temperature, this nice, straightforward formula doesn't work. And there are ways to kind of kludge it together, and sadly, many of those ways are partly built into your pH meter, so that you get this impression that in principle you could have done that. But I wouldn't bank on it. You can, but you add extra uncertainty by having your buffer and your sample at different temperatures. So probably this ought to be or would be a question for many of you. What on earth is a tris buffer in synthetic and where can I get it? Well, tris is a nice convenient way of saying 2-amino-2-hydroxymethyl-1,3-propane-diol, or trisaminomethane as it was once known. And it's a simple organic base, these amines. The acid form is essentially protonating one of those amine groups. It's got a pK of around 8.1 in seawater on a total hydrogen ion scale. That means the buffer's right there where you want it. That's really useful because if your electrode was not perfectly Nernstian, the size of that error will depend upon the difference in pH between your buffer and your sample. If they're the same, it didn't matter the electrode wasn't Nernstian. As you get further away, it does. So the fact that this has a pK in this region is very convenient. And a postdoc and I published a paper a few years ago here, the stability and reproducibility of tris buffer in synthetic seawater. Having made it, how long would it keep for was really what we were asking. And could you make it in bulk reliably and things like that. The problem is that tris buffer is in synthetic seawater. So to be a buffer, you've got to have the acid form, the tris with H on it, so one of these protonated. You've got to have the base form. To be a good buffer, they're going to be in approximately the same concentration each. A buffer means if I contaminated this with an acid or base, does the pH change a lot or a little? A good buffer, it changes a little. It's like you can imagine a thermostat bath or something that's holding temperature. A good thermostat bath, you can put something in it and it doesn't really change very much. What happens is the other thing comes to that temperature. If you put something into a buffered solution, it comes to that pH, the ratio of its acid and base forms. So you have to have those two, but we then had the phrase in synthetic seawater. I gave you the list: water, sodium, magnesium, calcium, potassium, chloride, sulfate. Gets a little ugly. This is the recipe. The reason I mentioned this paper for the recipe is I'm kind enough to tell you what you should weigh out to make 1 kilogram of solution. And this allows for the fact that when you weigh something, you're not actually measuring the mass of it, you're measuring its weight. That is, you've got the force due to gravity, but also the buoyancy due to air. And you have to make sure that these are adequately accounted for. The sad fact is that ideally, you'd like to put in known amounts of magnesium, calcium, and HCl, but you can't just buy those as crystals that you can weigh. They're all things that basically, to do it well, you have to do them as stock solutions, which means you have to calibrate the stock solutions. So when I have somebody come to my lab and say, we'd like to learn how to make our own pH buffers, I say, well, you have to plan to stay here a couple of weeks. And then they can go away having learned how to make them, because we show, how to get the salts, how to make up stock solutions, how to calibrate those well, even how to check that you ended up with a buffer that was about right. Here's the data from that paper showing the stability of the buffer. Reproducible. I made up 2 separate batches. Now this is a little more awkward. It's not so hard with a balance to weigh out weights approximating these in 1 kilogram of water. It's a little tougher when you want to make 20 liters of buffer, because then you want 20 kilograms. I don't have a balance good enough for that. So I actually have a 12 kilogram balance and put a bunch of like 10 liter bits of water in with a known amount. So they never end up quite the same. Second is clearly they do drift with time in the bottle. Third, if you look at the left-hand scale, not much. That's a very expanded scale for pH measurements. Now these are measured using a system a little different from the one I talked about, in that the reference electrode is directly measuring chloride ions, so there's no liquid junction. It's a silver-silver chloride electrode. The hydrogen-sensitive electrode is actually a hydrogen electrode. The beauty of that is that inherently that system calibrates very well in an acid solution, and therefore gives us this. So it's drifting of the order, a little bit more than 0.001 of a pH unit a year. So we've put a bunch of these in bottles, and they're available from my lab, or at least they will be again. The last ones were shipped by FedEx to Woods Hole yesterday afternoon. And we're going to start storing them we store them in these bottles because this is a fairly chemically resistant bottle. It probably would work better in a quartz bottle, but quartz bottles are stunningly expensive. And we certify it with a hydrogen electrode. So you can get a bottle of pH buffer. But this is the difficulty. If you're using electrodes, you always have to have a buffer there. And so you always have to calibrate. So probably you have to make up your own pH buffer. But if you got some of this, you compare the two and say, yeah, I made it up okay, or no, it's 0.01 higher than what it ought to be, but it's 0.01 higher yesterday and tomorrow, so I can allow for that. Probably you've got that because you got the ratio of tris to HCl, not perfectly 1-to-1, but slightly different because your HCl wasn't perfectly calibrated, your tris wasn't perfectly pure, who knows? If you get that ratio wrong, you'll get a different pH. But it'll still be a buffer. So this ability to cross-check your own measurement is there. So having done this, how well will you actually get pH measurements out of this? It's not as good as you might have hoped. First, the buffer itself. If it's not one that's been with hydrogen electrodes, probably the chance you made it up well enough is not very good. So it's going to be some larger number, but more than 5 1,000ths of a pH unit. Now we come to the next problem with this whole discussion of total hydrogen ion scales. Remember I said that the equilibrium constants are functions now of temperature, pressure, and salinity. The same is true for the buffer. You would like to have the salinity of your buffer match the salinity of your sample. Rest assured it won't. We make buffers that are a nominal 35 salinity. There's probably very few of you work in that particular part of the North Atlantic that gets to exactly that number. So if you're within 5 in salinity of that number, you're probably less than 0.1 in pH wrong in using that buffer. And it's a lot easier that way than trying to you can make up tris buffers at any salinity you choose, and the data exists to infer the correct pH for them. But unless you have hydrogen electrodes, it's difficult. If you're electrodes non-Nernstian? Well, if it's pretty good, 99% Nernstian, then the error in pH is always over the usual range, like 7.5 to 8.5, going to be less than 0.02. How would you know it's 99% Nernstian and not 75? Well, you know, your pH 4 and 7 buffers might tell you that reasonably, because that's supposed to be 180 millivolts. So, you know, you'd be almost 2 millivolts different. If those are good buffers, you can do it. That's often the only way is to check an electrode like that. My experience in my lab is that of the electrodes we buy, and we buy the more expensive electrodes, I mentioned the number $200-300. You could buy electrodes a lot cheaper, but buyer beware. With those more expensive ones, probably 1 in 10 is kind of at 99% as opposed to meaningfully better. The biggest way to mess up a pH measurement, however, is the poor sample handling. Because if you exchange CO2 with your sample and the atmosphere, gaining or losing, as Chris showed with his calculations yesterday, the pH necessarily changes. Not actually as much as you would fear, because it's a logarithmic scale. 0.01 looks like a nice tiny number, but that's, you know, almost 2.5% change in hydrogen ion concentration. So 2.5% change in PCO2 is about what it corresponds to. So, you know, given that this isn't that precise, the sample handling isn't quite as demanding as you might have feared. But it's still there. You can mess it up with poor sample handling. I would say, if I was picking a number out of a hat, and it's, you know, a hat with a limited number of balls in it to select, the overall uncertainty of an electrometric pH unit is of the order of 0.02. You could squeeze it better than that. But the bad news with all of these things is if you want a factor of 10 improvement in anything, it's a factor of 100 extra work in most cases. So you might not really want to do that. What does that mean? If you had a sample of a pH of 8.1 and an alkalinity of 2,300 micromoles per kilogram, canonical North Atlantic surface seawater as defined salinity, and you infer the total carbon, you're going to be about 10 wrong. That's 10 out of 2,100. Actually, a little less than 2,100. PCO2, you're going to be about 5% wrong. You'll be about 5% wrong whatever your pH is in the plausible range for seawater, and even seawater experiments up to about 1,000, PCO2 of 1,000. So if 5% in PCO2 is okay for you, then this is the cheap and cheerful way to make the measurement. It can get better. We can do it a different way. The way it's done most typically for oceanographic pH measurements is to use an indicator dye. Now, those of you that are privileged enough to have swimming pools but not privileged enough to have people to look after them for you will know that a colorimetric indicator is this colored liquid that you add it changes color, and the color it changes to tells you something about the pH. The most common one used in seawater is this one. These are the extinction coefficients for a dye, metacresol purple. And the one you're most interested in are these two peaks here, the 2 minus and the 1 minus peak. I write it with I as a moiety. The organic formula goes on for a couple of rings and a few other odds and ends. So a more complicated molecule, but the essence is it's an acid-base system. And because it's an acid-base system, everything we've seen before is true. That is, the pH depends upon the ratio of the base and acid forms of the dye and this calibration factor, the equilibrium constant. Now, the thing that made it an indicator was that the base and acid forms of the dye have different absorption coefficients, different extinction coefficients. They're different colors. So this ratio, as the ratio changes, you have basically purple paint, yellow paint. If you've got a little bit of purple and mostly yellow, it's a very, very pale purple. If you've got a lot of purple and hardly any yellow, it's a very, very deep purple. Your eye's okay at distinguishing that, but not really. Most of the ones designed for swimming pools give you a better one for your eye to look. But we're not going to do this with your eye. We're going to do this with a spectrophotometer. And with a spectrophotometer, we get a spectrum that's a composite of these two peaks. And from that, we can infer this ratio. And if we know this ratio and we knew the equilibrium constant, you would actually know the pH. So to know the ratio, what do you got to do? Well, first, you've got to get this picture. You've got to know how the dye is a wavelength-dependent absorption for a dye. How do you get this one? Well, you get it exactly the same way I said. You've got to have something that you know the pH of. Tris buffer in synthetic seawater. Carefully certified with hydrogen electrodes. If you do that, you know the pH, you know this, bam, we measured that for that salinity and temperature. Do it multiple times with multiple dyes that each took 3 days to calibrate. You got over a whole range of salinities. Temperature is more easy to handle. So to use this then, you just simply go forward. You say, okay, we're going to have, at any particular wavelength, the absorbance normalized with respect to how much path length of liquid you're looking through, 10 centimeter cell, 1 centimeter cell, 1 meter cell, is, loosely speaking, the sum of the extinction coefficient for this times its concentration plus the extinction coefficient for this at that wavelength times its concentration. If you make measurements at two separate wavelengths, and you have this formula which you knew, a small amount of middle school algebra with things that look more confusing than x's and y's ends you up with this equation. This equation is really what you should think it is. It's the one I've been talking about before here. Let's imagine that the terms I'm standing in front of you can't see, which for now is probably true. This ratio here is very obvious. It's simply saying that the ratio of the absorbances and the rate to the extinction coefficients. So that's telling me how much of that species is present at that wavelength. Because it's the product of the concentration and the extinction coefficient. We take two wavelengths, we can get a ratio. The unfortunate difficulty was that under this peak, we tend to do these measurements on the wavelengths corresponding to the peaks. Why? Because if your system doesn't measure with the wavelength very well, you don't actually get much error added by that. You could, in principle, take any two wavelengths, but it would be verging on careless to do one halfway down the peak, because the slightest problem with the wavelength, you've got a big change in the extinction coefficient. So it's usually on the peak, but under this peak, there's a tiny bit of this species. And under this peak, there's a meaningful amount of that species. All the other terms you're seeing in here on this side are essentially corrections for that gets in there. The basic idea is these first two terms, which dominate the expression, so that you can see how well you have to measure an absorbance or how well you have to measure an extinction coefficient to get an error in pH. You could just propagate the error through. Now, extinction coefficients, which are typically expressed as these ratios, not the absolute values. And this is convenient because the dye is not so straightforward to know how much of it you ever put in a particular solution. It's horribly darkly colored, a pain to weigh, and may have some impurities in. So ratios of extinction coefficients where you're fairly confident you based it on the same stock solution get you some help here. These extinction coefficients are weak functions of temperature. So what you hope is that somebody would measure them as a function of temperature, and you could look it up. And they have, and you can. That equilibrium constant dye is salinity, temperature, and pressure. And as I said, it's calibrated with a reference buffer. Now, you're going to see during this week how this is done. One of the ways that you started with yesterday was pointed out that you can fill a spectrophotometer cell with seawater. Having done that, what you would do is measure the absorbance for a background, i.e. what's the transmission going through the glass, the liquid sitting in the spectrophotometer. Then you'll put dye in it and measure it again. And from those two transmissions, the spectrophotometer will calculate for you the absorbance. And from the absorbance at different wavelengths, you'll get this ratio. There's other corrections because you took the cell out and you put it back and things aren't perfectly lined up. So we actually make a measurement at a third wavelength out here, which should be the same and should be almost nothing between your two things because it's not dependent upon the indicator being there. And if that changed slightly, you say, oh, that's because I didn't put the cell in quite right, or because the intensity of the light source has changed a little since I last did this. So I can make a correction based on that. And so you'll see that. I haven't included that in the equations here. You read the cookbook carefully, you'll see more gory detail. Just wanted to mention the way we do it in my lab, which is a somewhat more straightforward system once it works, as are they all, with that small caveat at the end, once it works. Essentially, we collect samples in a bottle. We have a syringe pump. We can suck sample into the syringe pump and pump it on through here. This is a temperature equilibrator to ensure that it comes to the temperature we're wanting to make the measurement, and into a cell which is typically sloped a little bit so that any of your bigger bubbles move up to the end and come out. Little ones can hang around on the surface. This is a custom-made cell, so it's not straightforward to get hold of. Having got this, you can get the background measurement. You can then do another one, add dye, partway through, suck in some sample, suck in some dye, on down, put through. You get the measurement with the dye. You can do the calculation. You can flush the system from a large jug of seawater to make sure that previous sample's gone out the way. Add the small amount of background from your last sample. So the idea here is cell was full of unknown seawater. Now you add your seawater, but you don't flush it as perfectly as you had before. Maybe it's 99% flushed. So the background is on 99% your sample plus 1% unknown seawater. Neither of them is supposed to absorb. The chance that you mess this up badly is small. The next one comes through, and it's 99% your sample with dye plus 99.99% of your sample plus 0.01% of who knows what that water was. The chance that the pH was wrong is slim too. And you repeat. About every 3 minutes, this can run a sample. Partly because the temperature, this gadget brings the temperature to within 1/10 of a degree, or 1 or 2/10 of a degree, before it ever goes into the cell. So it doesn't have to sit in the cell long to be at stable temperature. But then you need this bottle to be within about 5 degrees or 4 degrees of where you want to be. Otherwise it doesn't work. So we are writing this up currently. This is a graduate student of mine, Brendan Carter, and another graduate student there, Adam Radich. And we'll disclose its advantages and flaws reasonably soon. I think this has a lot to offer because it ends up like salinity measurement. You put the bottle on, you push the button on, you wait, a number comes out. pH. It uses about 50 mils at most of your sample. We can make it less. It's a matter of how thoroughly you want that flushing to go, because it doesn't have to be that thorough because of this junk water, rinse water line on it. So sources of uncertainty in doing it this way. Error in the pK of the dye. I think that's probably less than or equal to about 0.005 of a pH unit. With more care than has yet gone into it, we probably have it quite a bit less than that at 1 salinity and 1 temperature. But if you just look it up, what you can get in the literature, I think that's the kind of range of error that's there. The bad news at the moment is this. If you buy a lot of dye from Kodak or Fisher or something like that, its spectra will look exactly like I showed you if you only have a little picture like that. But if you look really carefully at the spectrum, you will find that there is batch-to-batch variability in those extinction coefficients. This should not be, right? If it was a pure chemical, it would have the same extinction coefficient if you did it on the same spectrophotometer, because those numbers have a piece of the optics in the spectrophotometer built into it as well. Second, this error looks, and there was a paper came out about a year and a bit ago, to be up to about 0.01 in pH. And it's not been resolved. So if you don't have a way of checking your dye better than that, you would be unduly optimistic to assume it was better than that. But you're adding a liquid, which is an acid-base system, to your seawater sample. As Chris pointed out yesterday, seawater is actually not in its best buffering region, even for the small amount of buffer substances that it has in it. It was at a pH where we had about a 10-to-1 of bicarbonate to carbonate doing the buffering. So probably there's going to be an error there. You can minimize this error. You can make this quite a bit less by carefully adjusting the pH of your dye stock solution, or by doing a series of experiments that allow you to allow for this. The chances that you necessarily do that all the time well enough are small, so that's where my number came from. Again, of course, poor sample handling. So the real push is that problem with extinction coefficients, and it holds it at that level, in my opinion, at the moment. That is the degree to which your pH and your equilibrium constants are necessarily defined the same way. There's an error here. There's an error in equilibrium constants too. So that's half the error we had before. This is actually, I think, perfectly good for many ocean acidification experiments. Perhaps not where you're trying to see natural changes and interpret them. But changes in pH are probably much, much better than this, because you're using the same dye. So it's the same lousy extinction coefficients. So the change is much more sensitive. If people measure the reproducibility of a pH measurement like this, the reproducibility is better than 1/1000th of a pH unit. That is, if you do the same bottle twice, they will agree such that the computed standard deviation is significantly less than 1/1000th of a pH unit, which is way better than this number I gave here. So if you're looking at changes in pH as being interpretable to you, this actually is a very sensitive method. My 0.01 here is a kind of absolute overall uncertainty. This is what the calculated PCO2 is. It contributes to it. Now, there are also other pH scales. And as I intimated before, not recommended. But let's cover it briefly. Two other scales have been used. An NBS scale. It's often referred to as an NBS scale. The same is now referred to as IUPAC, International Union of Pure and Applied Chemistry. It uses low ionic strength buffers, pH 4-ish is actually a buffer potassium hydrogen phthalate. It should be 4.008. You can do a mixture of two phosphates, a dihydrogen phosphate and a hydrogen phosphate. This has a pH of about 6.8. You can mix the rate, change the ratio a little bit, and it's called a blood buffer, which is like 7.4. You can have borax 9. Those are the most common, those four, but they're all low ionic strength, which means that that liquid junction between your chloride solution in the electrode and your actual sample changes when you move from the buffer to seawater. And so there's an added uncertainty in that because you don't know how much it changes. It depends on the design of liquid junction. So if you have 3 different designs of liquid junction and you put them all in the buffer and all in the seawater, you will get 3 different pHs. Very different? Mostly no, because most designs aren't that different. But some, the difference could be about 0.02 in pH, no trouble. Because of this change in liquid junction from a solution where we ended up, and it's a stable diffusion mixture of the buffer and the potassium chloride, we put it in seawater. Now all the ions have got to change and get to another stable configuration. It often can take a long time to get stable results. And that's a problem. So the advantage of this scale is everybody has it. You can buy the buffers anywhere. You can buy them from somewhere like Fisher Scientific, and they're not really well calibrated, but they tell you how well calibrated they are. You can buy them from the National Institute of Standards and Technology, the salts to make up the buffers, and they'll give you the recipe and the salts. It's a much easier recipe. Dissolve one thing in this amount of water or dissolve 2 things in this amount of water. It's much better than that tris, right? But you have an uncertainty built into this whenever you use it in seawater. Those of you that feel you have data that you still would like to rescue, we could talk about ways to characterize the size of that uncertainty with some uncertainty and get it around. But the real take-home message is this is not an ideal way to do it. It's convenient, and it's probably most convenient for just checking your pH electrode. Because if the electrode doesn't work in this, it's probably not going to work in seawater. And you can get 2 buffers of known pHs a decent distance apart, so you can look at the known slope of the electrode. The other scale, which is much more common, is this seawater scale. And essentially, it's exactly the same as the total scale I talked about, but has a more complicated medium. If your medium is thought of as including fluoride ion, then technically, in addition to H plus HSO4, you have to have plus HF. It becomes a little uglier to assign the pH to the buffers, but not much because of this, because you either have to have a more complicated solution or you have to just do it mathematically and say, I know what the equilibrium constant for the formation of HF is, and I can make the adjustment. My opinion is that this scale is fine, But the hard part you've got to be sure is that you're using a scale where your pH measurement and your measurement of, and the equilibrium constants you're using were done the same way. And that's not always so easy to track down. If you go with the total scale, you can look up constants in the guide that Chris and I published, and you'll see a whole recommendation there. Last is uncertainty of that's probably about 0.05. Remember 0.02 gave you 10% wrong with PCO2. 0.05, this is probably a bit beyond what you want anyway. Precision will always look a lot better. It always horrifies. I say, well, no, this is probably good to about 0.05. And they go, no, the precision was good. Look, 0.005. Well, yeah, but. And, you know, it's a long conversation, which on the whole you don't want to hear after you've made the measurements. So I suggest not making them in the first place. The uncertainty for this between 0.1 and 0.2, it's roughly the same as for the total scale. The difference is between them. pH on the MBS scale is about 0.15 different from pH on the total scale. On the seawater scale, about 0.01 different. If you use the constants from one scale and the pH from another scale, that's as though you made your pH measurement this amount wrong. 0.01, you might never know. 0.15, I hope you'd notice. That's a big change. There's about a 40% change in hydrogen ion concentration. So your PCO2s will be 40% wrong. So to summarize, pH cell, relatively cheap, pretty easy to use. Uncertainty is about 0.02, limited amounts of references. Spectrophotometry, mid-range. Yeah, you know, sadly compared to other CO2 measuring systems, maybe I could use the words relatively cheap there. But it can be very easy. Our system, I said, you push a button. But it took a little while to get it to that point. The uncertainty is 0.1 or below. We think we know ways to push it below that. This one we can't push down very straightforwardly. It's inherent in the design of electrodes and things. You probably, this might get to about 0.01. But I'm talking now, when I say uncertainty, is if I made a measurement here on the water and I had exactly the same water and I made it over here 3-4 months later, how really reliable would I know this with different electrodes, because I've broken the electrode I had before. So let's stop there before we go on to alkalinity, which will go at a faster pace, because pH, I think, was one of the more important. Any questions about pH?
So,
Yeah.
when you prepare the seawater buffers, calibrate that way, will that stop will that significantly reduce the drip time of the electrode?
Oh yeah, it's much, using a seawater buffer compared to a freshwater buffer, a 0.1 ionic strength buffer, the electrode comes to a stable reading, providing it's well thermostated much more quickly.
But you have to remember not to dip it into distilled water or squirt distilled water on the
Yeah, this is the thing. Essentially what you're really doing is you've got a piece of glass and it's got this sort of gel layer on the surface of hydrated glass. And you're taking it from a solution of one water activity and putting it in a solution of a different water activity. So that hydrated layer is changing. If you take that and you scour off the hydrated layer with a tissue and spray it down with deionized water, it doesn't matter that you were going from one. You wreck that hydrated layer going from one to the other. So you want to be gentle, very gentle. Just dab it and put it. Buffer. Don't worry about putting a small amount of contamination. The real contamination problem is going back to the seawater, because seawater is not well buffered. So there's where you want to be careful. But you can rinse it if you have to, but don't scrub it. That really is the worst case thing when transferring it across. Yeah?
What about pressure? Yesterday you said that pH is obviously sensitive to pressure. Do you control
If you are using a hydrogen electrode system, you have to control because there's big pressure constant. The actual fact is, yes, it's sensitive to pressure, but not at the level in which it changes day to day in the lab. If you were looking at deep water samples by having a probe that went deep, there are people that do this. I'd say their results are as yet not clearly interpretable because the calibration of those probes, and the problem is that the liquid junction side has a problem. So people are trying to work with probes that don't have a liquid junction and how well those can work. And the problem then is that when you have a pressure, if it mechanically distorts slightly, the EMFs change. And so you have to have pressure compensation effort. So a lot of it is really in the engineering design of the probe system to do this. And I'd say that's not been conquered. People have done it in the past, probably with about 0.03 to 0.05 in pH uncertainty. And it's impressive results, but it's not ideal yet. So at the moment, we can't easily measure pressure with probes, measure pH with probes down and know what we're talking about over a range of pressures. With spectrophotometry, there's been some work to do this because things, how do the extinction coefficients change with pressure, and people looking at this, not a lot, but some. How does the pK change with pressure? Don't yet know, because the way to do that is you have to have another solution that you already knew the pH on. And the only one you can do that for really is actually probably an acid, because it doesn't change when you change the pressure much, because of course the HSO4 is going to change a little bit. So the relationship of the total scale to the amount of acid you put in will change with pressure. But at the moment, that work's not been done. You can't get one. You would be on the very sort of state of the art if you wanted to start building one.
And in shallow waters, when you've got tidal changes and stuff?
Oh, that level of pressure is not a problem. You know, plus or minus 10 meters, absolutely no problem for any of these.
Do you envision any solution to the dye-batch variability problem?
Yes. The next question. Two possibilities are being examined. Number one is that there's a straightforward way to get a meaningful amount of purified dye that can then be distributed in the way we're distributing CO2 reference. And I believe that Bob Byrne's group at the University of South Florida have been looking at that. The other is, if you know what the pH of your tris buffer is really well, and you put the dye in it, then put it in that equation, you say, oh, it doesn't agree. But the equilibrium constant I know is pretty good. The pH I know was good. The absorbance measurements were good. I'll tweak the extinction coefficient ratio. You have to have confidence in all those other pieces. But in that situation, you could tweak that, adjust that extinction coefficient ratio. And much of the problem is accounted for by that. You can do that as a pragmatic way to do it, but you have to be very certain that all the other pieces were true. Otherwise, you're adjusting something that should never have been adjusted that much in the first place. Because then it should stay constant for your batch of dye all the way through until you opened another bottle, possibly even with another batch number on it. If it didn't, then something else wasn't constant. We've got about half an hour here, a little bit less. So this will go at a sufficiently satisfying speed to confuse you. Alkalinity, temperature and pressure independent. Why? That really, to my mind, is a number. And understanding why helps you understand what alkalinity does and doesn't give you. Another way of doing this, saying this, alkalinity, if you dissolve CO2 in seawater, total carbon goes up. pH goes down. PCO2 goes up. Alkalinity stays the same. How the hell did that happen? Well, you say, well, yeah, but, you know, look at that. It's not in the equation for CO2. Surely that's why it stays the same. And the answer is, you know, that's a kind of a shortcut way of thinking about it, but that's not quite this whole story. So what we're going to look at is what is this idea of alkalinity, and put my caution notice on, but I'll try and take it a little bit slowly. The difficulty we have is that everybody knows what something that's alkaline is, right? Alkali, it's potassium came from this. It was potash. It was this sort of slimy feeling on your hands when you touched it. Eventually you realize it was the higher pH end, the amount of hydroxide there. Most people think alkalinity, amount of hydroxide. And yet that formula I gave you, hydroxide was a tiny little piece of it, 10/2400ths. So let's look where we develop from this idea of hydroxide beyond. So you've got a mixture of sodium chloride and sodium hydroxide. And I've got a 2 millimolar hydroxide solution in a sodium chloride background. Now, what are the species present in this solution? Very easy to figure it out. There's these ones. There's hydrogen hydroxide, sodium chloride, there's water. Mass balance information. I know how much sodium I put in there. I know how much chloride I put in there. I can do a charge balance, which is that the sum of the concentrations of the positive ions have to be the same as that of the negative ions. I made this solution up from a water, sodium chloride, and sodium hydroxide. Now we can rearrange that charge balance equation like this. And in actual fact, what we find is that that difference is equal to this, which is the amount of NaOH we first put in there. So the alkalinity kind of made sense. It's the amount of alkali you put in. But it's temperature and pressure independent, because it's actually the difference in these two concentrations here, the sodium and the chloride, also. And although pKw will change, and the concentration of OH and the concentration of H will change as you change the temperature, those two don't change. So this composite doesn't change. That's the essence of the idea behind alkalinity. We get it a little uglier. We put CO2 in. So now we've got alkalinity and total CO2. This line got longer. We now have the CO2, 3 CO2 species in here as well. Mass balance information, same as before. Total carbon, we also know. Charge balance information. The positive ones, sodium, H+. The negative ones, weighted by the number of negative signs. It's a lot more. Rearrange that charge balance relationship. This grouping is now equal to those two. And therefore, must be that concentration. Because that's the amount, originally one could think of it, that's the amount of alkalinity you put in this solution. The fact that some of it is now taken up by carbonate species doesn't really matter. But the other is to say, the alkalinity is really this difference, the difference between the charge on the cations and anions. Again, you can change the temperature. Every one of these species concentrations is going to change. But these two aren't. So the sum defined like this doesn't change. You could do it by mixing something a little different. Let's just put it all out and then talk through it. I've put now bicarbonate in. Same set of species, mass balance information, same as before. Charge balance, same as before. So the implication of that is that we rearrange the charge, we've got the same thing. It has to be 0.002. And we look back and we see that that's actually the amount of bicarbonate we put in now. So before I'd put in CO2 and hydroxide, I'd separated adding my carbon and adding my hydroxide. Now let's imagine we're back in that original one with the CO2. Sorry. And we added more CO2. Instead of 2 millimoles, we added 4 millimoles. What would change? Well, first, those two would still be the same. Therefore, you'll have a charge balance like this, but when you rearrange it, this will be the same. So even though we add a lot more CO2, we didn't touch the alkalinity. That was dominated, understandably, because that was the amount of alkali I put in the solution. One can, of course, go through this, the next piece. Let's put sodium carbonate in. Same species. This is true. Total carbon's a little lower. Charge balance, exactly the same. .002 again. The difference in the sodium and the chloride concentrations. So the alkalinity here from putting the carbonate in, so we put CO2 in, we didn't change alkalinity. We put bicarbonate in, we changed it 1 mole per mole of bicarbonate we put in. We put carbonate in, we changed it by 2 moles per mole of carbonate we put in. So what really is this entity we're specifying moles for? Moles of alkalinity. Well, it's the moles of hydrogen ion whose charge is equivalent to that difference. And that's the idea behind alkalinity. Let's go a couple of steps more messier. Boric acid. We get more. This line gets longer and longer. Mass balance is there. Charge balance. So same problem we have with CO2, but I said, hey, throw in 400 micromoles of boric acid. If I put it in as boric acid, charge looks like that. Borate now is turned up here, but the alkalinity is still defined by that hydroxide equity. Now, think it through. If I put in sodium borate instead of boric acid, yes, I'd have added borate, but really I'd also have added sodium. So this would change. So the alkalinity would change. And it's that way of thinking about it that's a little different to the usual approach of why is it constant? It's constant because it's a linear combination of things that really are independent of temperature and pressure.
So can you explain why you're only putting the sodium and the chloride on the left?
Because
You have other positive and negative ions. Why wouldn't you put them on the left?
okay, that's clearly the piece I missed out in this discussion. What I've done here is I've grouped it where all the acid-base species are on this side and all the other species in a charge balance expression are on this side. So that's I've rearranged the charge balance to put all the acid-base species on one side and the non-acid-base species on the other side.
Or you can say conservative and non-conservative on it?
Boron is, I mean, yeah, when they're obviously you change the temperature, they change. They're not stable concentrations. So for seawater, of course, it gets uglier yet. But we define this total alkalinity this way. It's an equation that you've sort of seen coming out before. And you could rearrange that, and it's this. So the alkalinity is equal to this. Therefore, it's, you ask yourself what happens if you add CO2. Well, same as before. You add CO2, you weren't changing any of those red numbers. But
Even though sulfuric acid is an acid base.
But if you added sulfuric acid, you're changing this number. If you're adding HCl, you're changing this number. So if you add HCl, the alkalinity goes down because the chloride went up. If you added sodium chloride, yes, this went up, but so did this, the same amount. So it didn't change. Now, add or remove calcium carbonate. You could think of it as removing this term here, changing this concentration. So it's going to change alkalinity. You add it, dissolve calcium carbonate, alkalinity goes up, like when I had sodium carbonate there. Right. Now, this is a convenient way of thinking about it, and there's a paper discussing this, and I'll give you the reference momentarily. But this is really why this weird combination of terms comes up. It's a combination of mass balance and charge balance equations. I think it's fair to say that there's an infinite number of possible combinations of mass balance and charge balance, which also would have this property. This is convenient because you can measure it. And you can, yeah?
Can you go back to that equation? He had brought it up, but I don't think I got the answer. The sulfate, as you mentioned, was an acid base. Why isn't it on like the other side? It can't be an acid base, and it's instead of the sodium magnesium.
Okay, you're quite right. But bear in mind that technically, this term here, H plus, is H plus HSO4. And so it's in there implicitly because of our decision to label these concentrations as total concentrations. There will be a point in a few minutes where I untangle it a little because to do the most precise measurements, you have to. So you can measure this by titrating. And the whole goal is you're trying to find an equivalence point where the equivalence point is where this is equal to 0. That is, you've added enough acid such that the alkalinity has gone away. If you add more acid, you get negative alkalinity. It's one of those unusual concentrations where it's totally meaningful to have a negative amount of the stuff there. That's not so good for sodium. But here, a negative alkalinity means you've got excess acid. So what you're doing with the titration is trying to get to the point, how much acid does it take to get that to 0? If that's 0, then we can rearrange it in this form. And this kind of expression is called a proton condition. And you can derive it, as I have done before, it's the kind of mass balance with charge balance relative to these three species. And the advantage, I said, if I add more CO2, it doesn't change. If I add more boric acid, it wouldn't change it. I could have chosen three other species here. I could have had it water, bicarbonate ion, and borate ion. I'd have got a different expression that would still be temperature and pressure independent, but wouldn't be so straightforward to measure. This can be measured because we can add acid to the system where we've got that zero. So where is that zero? Well, let's go back to this picture. It's zero is when that top equation is true. Well, let's say where H, if we just had the first two terms, H equals bicarbonate, it would be this crossover point here, right? Well, at that point, in actual fact, the carbonate ion concentration is a lot less, so two bits of that aren't going to move our pH at which that's happening very much. The borate concentration is a little bit more, but still, you know, almost 100 times less than the bicarbonate concentration. You know, a couple of hundred almost. Hydroxide, the red line, about the same as the carbonate. The hydrogen ion was there. So what you actually say is, I'm trying to find this point. And the essence is you titrate seawater, you measure how the hydrogen ion concentration changes as you add more acid, that is, as you change the alkalinity. And you keep going until you sweep through this pH range. And then, in actual fact, it's much easier to use the data from this side to backtrack to where that purple line ought to be, because over here, a whole bunch of these terms become so small that errors in them become irrelevant. The approach we actually take to do this is we also purge our solution of CO2. We acidify it, get rid of the CO2, which means these green lines also come down. And then we go back, and it's much more straightforward to do that calculation. Or actually, we go on doing that calculation. But doing this computation is somewhat ugly. You could look in this, and you would find out how to do it. And it's straightforward in that it's algebra and a computer program, but it's ugly. So, is alkalinity really how I defined it? Not quite. I defined it many years ago. I said, well, gee, yeah, this makes sense, but what happens if there's phosphate in the water, or ammonia, or HS, or and it was better to say, okay, let's choose how we're going to do that. And this is a matter of choosing which those species are in a proton condition, which is another way of thinking about this. I wrote this as a definition. This is an arbitrary definition. That is, this number, 4.5 at 25 degrees centigrade and 0 ionic strength, is picked purely such that at this pH, species dominate in the way you would expect, so it's easy to do the arithmetic. But you could choose that number anywhere else and define a different alkalinity. People have. You will see at least two versions of alkalinity, sadly. One that looks like this, and one where the terms for phosphoric acid are a bit different. If you look at this, because of this choice of K of 10 to the minus 4.5, the neutral species for phosphate is actually the H2PO4 minus species. So that's the one that doesn't appear in this equation. The acid, H3PO4 does, HPO4 does, PO4 does. So the weights are not the charges. The weights are actually not the charges, they're how far they are away from that zero species. You will see in many papers particularly from the 1970s, a different version of this equation where phosphate is handled differently. So if you get alkalinity that those people reported and you process it with CO2 cis, it will necessarily give you a wrong answer. They reported what they said they'd measured. The other thing is that, of course, this gets, if we limit it to the ones that are the higher concentration species, it looks like this. And as I said before, those two are really that H+. Now, implications. Well, number one is that when I process the titration in my lab, I actually ignore everything on this picture except for alkalinity and these three terms here. And the reason is I've got rid of CO2, so the CO2 terms disappear, and the others are at such low concentration at those low pHs. And I can get an accurate alkalinity. This is a matter of, probably should have an extra little skull and crossbones on it. You will get an accurate alkalinity, probably, for any seawater sample you take and titrate. But you don't really care what the alkalinity was for many purposes. Sometimes you care what the change in alkalinity was because there's a geochemical process changing alkalinity. But if you want to use that alkalinity to calculate carbonate ion concentration, then ultimately what you're going to do is say, I think I can correct for everything in this equation except for carbonate. And to do that, you had to know the total concentrations and the Ks, the equilibrium constants, for all those other species. So if you're in a culture medium that you've added some joy juice to in the form of nutrients to speed up growth, this is a problem because these things are changing all the time. They're being taken up. So the alkalinity is going to change just because things grew anyway. And interpreting alkalinity changes is the hard part. Measuring it is not. You'll actually get a stable one. It gets worse yet. We can have organic acids present. That equation had an interesting couple of terms. ... Something left out here. Who knows what? And the next candidate is organic acids. It's an interesting history. In the good old days, early 20s, before the Second World War, 1920s, alkalinity was defined as an idea. It really just had those two terms, the carbonate contribution to alkalinity. Then somebody said, this really doesn't seem to be working. And they said, there's boron in seawater. So it's this term. Then people got to be able to measure alkalinity more accurately and said it's still not working. Maybe it's phosphate. Maybe there's a lot of phosphate in seawater. It wasn't a lot of phosphate in seawater. There typically isn't. What they actually had was the equilibrium constants were wrong. That's why it didn't work. But the next things people added in were phosphates, all these. So ... all the things I haven't yet thought of. And organic acids is one. We basically have shown that in systems with significant biological activity, sadly, maybe even systems where you're growing things to study their biological activity, you can get organic acids with a measurable contribution to the total alkalinity. Postdoc and I had a paper that addressed this. So how would you know? Well, the only way you're going to know is if you calculate the alkalinity from carbonate and borate and things, and you measure pH and you measure total carbon to do that, and you measure the alkalinity and the difference, you go, whoa, it's bigger than I expected. Either you measured something wrong or ... is there. And this is the difficulty. You can't say this necessarily is a problem without doing extra measurements. So my simplistic advice, as I say, is this, that alkalinity measurement has a real advantage. It's relatively cheap. It's pretty stable. It can work well. Our work in open ocean chemistry studies has really shown how well you can do alkalinity. I believe my lab routinely is doing it in the lab with an overall uncertainty of a little bit bigger than 1 micromole per kilogram. Our precision is, a factor 2 better than that. But if you're in a productive system, don't use it. You're going to confuse yourself more. Now, there are times you say, but I'm studying calcification. I have to study alkalinity. Well, consider it as a third parameter, would be my suggestion. Because as I say, how would you know? If you measure pH and total carbon, predict alkalinity, compare it to your measured one, you should worry about a significant discrepancy. Significant is in the eye of the beholder. Because, how big a discrepancy becomes important to you. Often, you will see changes in alkalinity that are understandable with a little bit of thinking about as related to changes in calcification. Now, alkalinity is another one that I could have put this has been a confused area of marine chemistry. I wrote a brief history of it a number of years ago.
Andrew, before you go on.
Yeah.
So if you have organic acids in your solution,
Yeah.
why doesn't that also affect the pH?
Because the pH is simply a measure of the acid to base ratios. Will it change the pH? Oh yeah. But if, no, if you measure the pH, that's telling you the ratio of bicarbonate to CO2. If you measure total CO2, you can now calculate what the amount of CO2 present as carbonate ion, as bicarbonate ion, and as pH. If they put organic acids into the water and change the composition, they will change, you're right, all those ratios. But you will have measured it correctly if you measured pH correctly and if you measured total carbon correctly. Is it as controlled as tightly as you wanted? Sadly, perhaps not. So I think you measure, this is the difference between three things. What did you want it to be? What did you measure it to be? And how could you use those measurements effectively? What else did you have to know to do it? And with alkalinity, you lose out because you have to know so much extra to get the full benefit of it in a solution that's got a lot of other acid-base systems in there.
Well, but you're not necessarily measuring pH just for pH's sake.
No, that's why I say measure pH and total carbon. I'm measuring pH in order to calculate stuff from total carbon, i.e. the relative proportions of the species making up total carbon. And that's independent of all the other acid-base systems in there because the kinetics of acid-base reactions are so fast. They are all at equilibrium, and the pH is this master variable that you think is proportional to all those ratios. So, as I said, history. You can go back to this explicit conservative expression, its application to biogeochemical processes. And Dieter Wolf Gladrow and Richard Siebe and others talk about it here. This goes through a lot of biochemical processes and said, if you're taking up nitrate, how does it change alkalinity? If you're taking up ammonia, how does it change alkalinity? So there's a whole bunch of that covered in this paper. This is fairly good. What I've given you here is enough of a background to actually go in and read this paper. Without that, I think this is probably a little advanced. And just as a final note, just to point out why we're here, the change in pH. But these are not pH measurements. These are actually measurements of total carbon and total alkalinity on samples collected and sent back to Scripps and analyzed at Scripps. And the pH is then calculated at the in situ temperature. So there's some seasonal pattern related in part to that. But what I wanted to show you is that even though you measure Don't get hooked on, I have to measure pH, I'm studying acidification. Think of it as a means to an end. Here, with clean seawater, with total carbon and alkalinity, we get very sensitive variability in pH. Completely interpretable at this level. Now, to be fair, it might be that this whole bunch ought to be up a little or down a little because the equilibrium constants aren't perfectly known. But that affects all of them because these are all roughly the same salinity sample and roughly the same temperature. So affects each one point about the same amount. So you can get information about change in pH from these other measurements, including alkalinity, in good situations. It works the other way. If you've got pH, you can get information about alkalinity. You have to start worrying about the errors in both. And that's what I'll talk about more tomorrow. Yes?
Make one comment on your organic acids, and it comes back to yesterday talking about the sampling bags. From our measurements, looking at different storage things, a lot of plastics, polyethylenes in particular, give off formic and acetic acid as you store seawater in them. And so kind of this drift in alkalinity being stored in bags maybe.
Yeah, if you were to add formic acid to seawater, you would be reducing the alkalinity.
Right, but the drift that
So,
we were
no.
talking about yesterday in
Right.
in the bags.
Yeah, it could well be that you know, that a particular batch of plastic gave off more of that than previous ones had. Okay, coffee, I'm sure is waiting for you.
Back here.
And then you have a TV show.